Welcome everyone to tonight's presentations. Thank you all for being here. We have two very interesting talks lined up. First tonight, we will hear from Frank DiCicco, who will be talking to us about using geospatial visualization to determine tornado warning polygon accuracy. Can we save more lives? So Frank, if you want to share your screen and begin at your leisure.
Yep. Second here, I wasn't prepared to share my screen, so give me a second here to get the presentation open. 1 second. I apologize for the delay.
No problem.
We've got plenty of time.
Already messing up.
Not at all.
Alrighty. So, let me share my screen here. Okay, and I'll pop this into presentation mode.
All right, we see your screen.
Okay.
We're in.
Everything looks good.
Good luck.
All right, perfect. Okay, well, good evening, everyone. My name is Frank DiCicco, and tonight I will be talking to you about using geospatial visualization to determine tornado warning polygon accuracy. Can we save more lives? So why tornadoes? Well, we all have some experience with tornadoes, whether that be from films like The Wizard of Oz or Twister, or more up close and personal encounters. Personally, I've always been enamored with severe weather and tornadoes in particular. The fascination really began with watching hours of the Weather Channel over my summer vacations, and that's kind of morphed into me becoming an amateur storm chaser. While I find severe storms and tornadoes beautiful to behold, it's not lost on me that these are incredibly dangerous and life-threatening situations. And it may be possible for tornado forecasts to be more accurate. And this is why I've decided to analyze tornadoes for my capstone project. During tonight's presentation, I'll begin with an introduction and background on tornadoes. I'll also discuss the human impacts of tornadoes and briefly describe the tornado warning system. Before discussing the specifics of my project, I'll give an overview of tornado outbreaks. And then the second half of the presentation will focus on my project, specifically on the objectives, methods, and anticipated results. On average, the US experiences roughly 1,000 tornadoes per year, which is over 900 more than the next closest country. The map on the right is a point density distribution of tornadoes between 1950 and 2019. This is using data from NOAA. You can see the highest frequency of tornadoes is found in the middle of the country, concentrated in what is known as Tornado Alley. The US is in a unique geographical position where cool, dry air from the north collides with moist, warm air from the Gulf, creating the recipe for severe storms that spawn tornadoes, with the highest density seen in and around the area of Kansas, Oklahoma, and Texas. So now that we know where tornadoes are and why they impact the United States, how does this translate to people? Tornadoes account for roughly $400 million in property damage annually, along with 80 deaths and 1,500 injuries. Other factors are important to consider in relation to tornado impact. For example, studies have found that tornadoes that occur at night are twice as deadly as those that occur during daylight hours. With all this in mind, it's worth noting that over the course of tornado record keeping, injuries and fatalities due to tornadoes have decreased. So what is a tornado warning? A tornado warning is issued by the National Weather Service when a tornado is indicated either through spotter networks or on radar. Typical warning duration usually lasts around 30 minutes. However, the sequence of events leading to a tornado warning is very complicated, as seen in the flow chart in the upper right-hand corner of the slide. The first tornado warning was issued in 1948, and from that time until 2017, warning polygons were based on county boundaries. So what that means is that every point in a county would have been under a tornado warning, even if parts of the county were not at risk. However, in 2017, the warning polygon was modified to be storm-based, meaning that only areas that were directly at risk of being impacted by a tornado were warned. And we can see an example of this in the lower right-hand corner of the slide, where a tornado warning polygon identified by the red boundary has been issued ahead of the approaching storm. We can see the hook echo on the radar, which is likely the reason that the warning was issued. It's also worth noting that warning lead times for tornadoes drastically increased from about 5 minutes in 1986 to an average of 13 minutes in 2004. So how do we measure the accuracy of a tornado warning? The National Weather Service adheres to dichotomous statistics for accuracy of their forecasts. So a dichotomous forecast says that yes, an event will happen, or no, the event will not happen. In the table below, we can see an example of a dichotomous forecast. And what that table shows is that a hit means that an event is forecast to occur and did occur. A miss is an event that was forecast not to occur, but did occur. There's also false alarms, which are events that are forecast to occur, but did not occur. And there's also a correct negative, where an event was forecast not to occur, but did occur. So the National Weather Service uses two metrics to determine tornado warning accuracy. These are the false alarm ratio and point of detection. False alarm ratio, or FAR, is the fraction of predicted events that did not occur. For tornado warnings, FAR is 0.76, or about 1 in every 4 warnings are associated with observed tornadoes. Interestingly, FAR is much higher for other severe weather events, and that's indicating how difficult it is to forecast tornadoes. A point of detection, or POD, is the fraction of observed events that were correctly forecasted. It is possible to increase POD by increasing tornado warnings for every storm. What that means is that there could lead to a cry wolf effect, where the public would simply ignore the tornado warnings, and that's not something that we want. FAR and POD should be used together, as POD is sensitive to hits but ignores the false alarms, while FAR is sensitive to hits but ignores the misses. We can see the equations for FAR and POD on the right-hand portion of the slide. It's also worth noting that there are more complex dichotomous statistics like the Heidke skill score and Pierce's skill score. These equations are just simply using hits and misses in various ways that determine forecast accuracy. So what is the best way to warn the public? In my research, I found that there's a gap existing in studies around the geospatial accuracy of tornado warning polygons. And the reason for that is it is complicated. So what is a miss? As seen below, we have 2 images of a tornado strike. Both of these would be considered misses by the National Weather Service. However, on the left, we see an observed tornado without a tornado warning polygon. On the right-hand side, we can see a warning polygon was issued, but the tornado actually struck outside of the warning area, and the stars are indicating where that tornado would have been. So are these misses equal? It's also important to note that tornadoes move. A tornado could strike an area with an expired warning polygon, or it can move in the direction that misses the warned area completely. Additionally, the timing of warnings is important. Is the warning early or late in relation to the observed tornado? So all this needs to be considered in how complicated it is to forecast tornadoes and predicting their location. So I'm performing this analysis to help to try to protect people. With that in mind, it's important to define what makes a missed forecast impactful. Tornadoes in areas with no people don't have the same impact as tornadoes that strike large metropolitan areas. I've included images of papers to show that there is significant research around how people react to tornado warnings. There's many factors that influence how people respond to a tornado warning. These can include exposure to false alarms, over-testing of tornado warning sirens, community knowledge of the geographical region. An example of this would just be people thinking that tornadoes simply don't hit where they live, and the perception of the danger associated with a tornado warning polygon, amongst many other factors. As previously mentioned, things like the time of day are very important in terms of tornado impact, but other factors do need to be considered. So when taking all this into account, this means that it's very complicated to assess the human impact of tornadoes. One particularly interesting phenomena are tornado outbreaks. While there's no official definition of a tornado outbreak, An outbreak typically experiences 6 to 10 or more tornadoes associated with the same storm system. Tornado outbreaks usually occur within the same day, but they can also span several days. However, what we don't know is if tornado outbreaks cause the most casualties and damage, and this is where my project is going to focus. So the aim of my study is to assess geospatial accuracy of National Weather Service tornado warning polygons during tornado outbreaks and the link to human impacts. The specific objectives of my project include examining the relationship between tornado outbreaks and casualties and damage. Additionally, using case studies of tornado outbreaks, I intend to visualize tornado paths and warning polygons. Also, my study will apply dichotomous statistics to tornado warning polygons in relation to observed tornadoes. And then finally, I'll use this data to explore the link to human impacts. This is not a series of anecdotes. Rather, I'm going to be using a formal case study approach. With this in mind, I selected 3 of the most notable tornado outbreaks for use in my project. First, the 2011 super outbreak, which caused 360 confirmed tornadoes, $10.2 billion in damage, and 324 deaths. Next, I selected the 2020 Easter outbreak, having 140 confirmed tornadoes, $3 billion in damage, and 32 deaths. And finally, the May 2011 outbreak, containing 241 confirmed tornadoes, $7 billion in damage, 181 deaths, and including the famous, or should I say infamous, Joplin, Missouri tornado. The data for my project will include initial tornado touchdown points and tornado paths collected from NOAA's Storm Prediction Center. The maps below show the data in Esri desktop tools. The data set spans from 1950 through 2019 and includes fatalities, magnitude, and damage within the metadata. The data set has interesting features and trends. It includes an increase in lower magnitude tornadoes throughout the data set. However, it's unclear if this is due to an increased spotter network or enhanced radar, but it is important because it does influence the NWS statistics. The final data set was collected from Mesonet. I was able to download tornado warning polygons from 2011 and 2020 specifically and display them within the Esri desktop tools as seen in the image below. Of note is that the 2011 warning polygons were the county-based warnings, while the 2020 warnings were migrated to the storm-based polygons. And because of this, you can see some difference between the years. The metadata includes beginning and end time of tornado warnings, the date, and the closest radar to the warning. Will be also important to consider other data sources, including news reports, population and demographic information during the analysis. So this flow chart shows the methods I'll be using to conduct my analysis. So first, I'll need to gather the data from NOAA and Mesonet, which is already complete as denoted by the green box and seen on the couple slides before. Next, the data will need to be joined. Tornado points and paths have unique identifiers, making the join quite simple. However, there is no unique identifier that can obviously be used to join the tornado warning polygons. To solve this, it is possible to manually join the data. Another possibility would be convert the layers to rasters and perform the analysis using raster overlay methods. Next, I'll need to symbolize the data, which also is complete as seen by the green box. And then with the data prepared, I can now perform various spatial analysis to explore the data for trends and features. This analysis will include heat maps, point pattern analysis, and other spatial analysis tools. At this point, I'll use 2 different methods to explore and analyze the data further. First, the top path in the workflow details exploring the tornadoes by outbreak. I'm going to attempt to identify all of the tornadoes associated with outbreaks and those that were not. If that's possible and the data is prepared, I'll perform a regression analysis on the damage versus death and produce the results of the analysis. The bottom path of the workflow is the case study analysis. I'll begin by extracting all the tornadoes, paths, and warnings associated with each of the three outbreak case studies highlighted earlier. Then based on each outbreak, I'll apply statistics to each case study and produce the results of the analysis while creating 3 maps for each outbreak case study. And my anticipated results will be an exploration of the accuracy of tornado warning polygons during outbreaks for 3 case studies and link those to human impact. Next will be a geospatial display of warned versus unwarned tornadoes and the link to casualties and deaths. And finally, a general analysis of the relationship between tornado outbreaks and casualties. And with that, I will open it up to questions.
All right, thanks, Frank. Good job. Good job. If you will write your questions into the chat window, and Frank, as they come in, you can read them and respond in kind. While we're waiting for some questions, I actually have experience working with that same tornado data set. One of the problems that I had was trying to, because it'll give you the coordinate where the tornado touched down and then where it lifted off. One thing I was thinking about while you were going through your talk was, are you going to develop any kind of an accuracy measurement? In other words, if the path goes through the warning box, is that like a good result versus if it misses the warning box?
Yeah, right. So that was one thing that I had been thinking about. And as I was looking at the data in a preliminary fashion, I actually had an image that I decided at the last second to pull out of the presentation, but it was of a scenario similar to what you're talking about, where the path of a tornado just kind of clips the corner of a warning polygon. And what do you do with that? Is that considered a hit? Is that considered a miss? So I think there's going to have to be some, some decisions that I make there in terms of what to include and what not to include. But yeah, that's something that I've been considering as I've been looking through the data.
Yeah. Yes, that's a good point.
Yep. So yeah, I think I guess the answer to your question is I'm still considering it and figuring out what exactly how to handle it and what to do with it.
Okay, good. Looks like you have a question.
Okay, where's the chat at?
Actually popped 2 questions in there.
Am I not?
If you stop sharing, you might be able to see it better.
Yeah. Okay, here we go. Yep. Stop sharing. There we go. Much better. Okay, so do you have any ideas for accounting for improvements in the observing networks, NextRad satellites, increased number of spotters? We try to account for lead times, in other words, the amount of time between issuance and the warning. So for the first part of that question, so let me talk about NextRad a little bit first. I'd considered NextRad in some of this analysis, but part of the problem is going to be is if I'm focusing on tornado outbreaks in the case studies, I don't know how useful NextRad is going to be because their outbreaks are over a longer period of time, and what do you really do with a NextRad image in that case? If we were focused on something like, say, the Joplin tornado, where it's one point in time, it might be useful. In terms of accounting for improvements in the observed networks, it's something that I mentioned over time. There's definitely an increased number of spotters. Yeah, I mean, if the case studies that I identified are 2 from 2011 and 1 from 2020, so that's kind of going to be within that realm of time where we know that there's an increased number of spotters, but these are outbreaks, so. I think where you would see a difference in spotter numbers would be in those times where you're finding just a random tornado or a couple tornadoes out in the middle of Nebraska. I don't know how much impact that would have on say a tornado outbreak on a day where you're expecting a whole bunch of tornadoes.
So you actually, if I can interrupt, you lead into another issue as a meteorologist I've had many discussions on. How do you know if the Weather Service's data set accounts for double spotting, right? So if you and I are reporting on the same tornado, but it's traveled, are they accounting for that? And so I'd want to say yes, but I think that's at least a caveat to have in the final analysis.
Sure. Yeah, and it's something in the brief exploration of the data, the tornadoes do have unique identifiers. So my assumption is that they're accounting for each one of those tornadoes as a unique entity. But it's a good point, and it's something that I'll have to double check on and make sure that there aren't double counts in that data anywhere.
Yeah, it's definitely something to comb through. They do some fantastic work on QCing their data before publishing, but
Oh yeah, I'm sure.
It's definitely challenging. And I actually spoke with a warning coordination meteorologist who said, and I quote, satellites are not tornado detection tools. So yeah, if that question ever gets posed to you again,
Okay.
it's good to warn. It's good for issuing the watch, but definitely not the warning.
Okay. Good note. All right. So let's see here. Looks like, did I cover everything from that first question there? Are we?
Yes.
Okay, cool. So next question looks like from George, live in South Texas and experience some tornadoes at night. I've heard, and I think you addressed tornadoes in Texas at night are more deadly because people don't see them coming. How do you account for the difference in having tornadoes in the daytime versus the nighttime? So yeah, I think that's one of the things that it will be potentially explored in the analysis and part of the human impact on that. And one of the reasons that I chose the 2020 Easter outbreak is that there were quite a number of nighttime tornadoes in the Southwest, and they were particularly deadly. So trying to determine, maybe what are the reasons behind that? Is it, as you mentioned, that people don't see them, or how are the warnings being disseminated? Are people not getting the warnings in time and not, seeking protective action due to those warnings? So yeah, it's definitely something that I have to consider here in the analysis.
Our tornado sirens actually never went off during one of the worst times
Really?
the tornadoes came through. I think they're set off manually, probably because, I think we had the warnings because I remember seeing it on television, but I think without people seeing them, I'm not certain they actually that might have been the reason they never set off the actual alarms in the town.
Yeah, that's interesting. And that's not something I came across in any of my research was, how are the tornado warning sirens activated? I'd have to imagine that they would be human, there would be human intervention there. But yeah, that's an interesting topic that you bring up there. So yeah, I mean, I think the answer to your question is it's definitely something that I have to account for and would like to include in the analysis.
And to jump in again there, Frank, I think that's where in my second question, you can account for when the watch was issued to when the warning was issued. Because remember, the watch is all the ingredients are there, but we haven't spotted it yet. And the warning is, hey, there's a tornado. So yeah, it could have been, with those incidences that are quote unquote more deadly at night, people are just tired of watching.
Yeah, complacency could play a factor there for sure.
No, absolutely. And that's, the huge discussion on that at this year's AMS meeting this past January. So lots of good discussions to come through if you have a chance.
Yeah, I'm certainly interested in diving in here and finding all that I can about it. It's a topic that I'm passionate about. So definitely am interested in all that information. All right, George, did that cover your question there?
Yeah, that was very good. Thank you.
Okay. So I see Helen sent me a question here. So why do you think a case study approach will be useful in answering some of these complexities? I'd say that focusing on case studies, because these are, number one, they're smaller events, so you can really focus on a particular number of tornadoes that are particularly impactful in terms of casualties and damage, and And then I just blanked here. I apologize. Yeah, no, being able to pull the data out of a larger data set and look at smaller trends across unique or not unique, but specific incidences will help to really narrow down some of those complexities that you could see across the larger the larger data set. Especially in terms of some EF0s and EF1 tornadoes that are just kind of hanging out there and in the middle of the country here. We're really going to be focusing on impactful events that are largely covered, and there's a good amount of data and probably some more factual or some more accurate data about those events. All right. Looks like Jeremy has a question here. You may have said this while presenting and I may have missed it. Where do you obtain the death counts from? I wouldn't think that's an attribute in the path or hit location. It actually is included in there in the NOAA data set. One of the data fields is fatalities. Damage is also included in there, and that's in USD. So yeah, I was a little bit, when I first came up with this idea for this topic, that was one of the things that I was a little bit concerned about was, will it be, it's kind of grim to say, but will it be easy to obtain the fatality counts in these tornadoes? But NOAA does have it in that data set. One of the things that, and Fritz kind of alluded to something along the lines here of when you're talking about a path of a tornado, well, where do those fatalities occur across that path of the tornado? And that's one thing that I also need to think about in this analysis is, the path of a tornado could span several miles, and are all those deaths equally spread out across the span of the tornado, or are they concentrated in one area across that path? So it's a good question. But yeah, that information is in that metadata that I obtained from NOAA. So Jeremy, is that, yeah, I see the morbid question. No, yeah, no, it's a good question because it's something that I thought about. So all good there. Looks like Gerald has a question. If you find a problem with the tornado warning polygon accuracy, what information might be available to change the current modeling of polygons? That's a good question. I haven't really thought about, methods to change the way that a polygon is issued. The way that they're doing it now based on the storm-based polygons is definitely an improvement rather than just having a whole county warned and parts of that county not even being at risk. So yeah, it's not something that I really thought about as of now, but it's a good point and maybe something that could be included in the output of this analysis, is if there's any way that jumps out or that is easily discernible from the data to improve those polygons could be something that could be a suggestion out of the final analysis.
All right. Yeah, a lot of great questions. That's
yeah, it was good.
Awesome. So thanks everyone on getting good questions to Frank. Great job. Thanks again. Next up, Kenneth Krager is going to be talking to us this evening on spatiotemporal analysis of Greenland's climate. And he is up. We see your screen. You're good to go.
Fantastic. And just FYI, Frank, I popped one last question. It's more of something for you to consider as you keep going along. Fun fact, I actually did my undergrad research project on a tornadic outbreak in Atlanta in 2007. So you're speaking to a severe weather enthusiast as well. So good evening, everyone. Kenny Krager here. I'll be presenting my preliminary findings of my spatiotemporal analysis of Greenland's climate. I've always wanted to be a meteorologist ever since I grew up. The Navy made me fall in love with oceanography. So combined, as I've gone through GIS, I've also been able to delve into climate, especially in the cryosphere. And the Arctic holds kind of a near and dear place in my heart, coming from the Navy and knowing just the treasure trove of resources and the economic impacts of having the Arctic open up, especially in the summers in the future. But Greenland's climate in particular poses some very, I'll say, interesting threats, to keep it at a less than morbid level for our future climate. So my analysis is going to be more exploratory and less explanatory. The explanatory type research is definitely more in the realm of a doctoral dissertation. So we're sticking with the let's see what's going on in space and time. So I've already started discussing a little bit of my motivation, but here we have the rest of what I plan to discuss with y'all. So again, there is an incredible amount of research going on in Greenland's climate, since in the northern hemisphere, the Greenland ice sheet is probably the biggest chunk of land ice that we absolutely must be concerned about. Because as that melts, that's going to lead into changes in global climate or weather patterns. It's going to lead to increases in sea level and so on and so forth, and all the second, third, fourth order effects of these changes. But again, my analysis is really just looking at a couple key parameters, key meteorological parameters, and how they've changed over space and time, just see what's happening, to, again, more explore what's happened in the last 40 years and less try to explain it. So I am using strictly the R statistical computing language. In prior classes and prior coursework, ArcGIS and these massive NetCDF files of environmental data do not get along. But I found that R usually handles environmental data pretty well. So I'm working through spatial point pattern analyses. I'll be getting to spectral analyses to pick apart trends in time, and I'll be conducting spatiotemporal analyses to include some exploratory modeling to explore potential relationships between these parameters to try and see what kind of statistically significant trends exist in space and time. And for anybody who doesn't normally exist in the world of climate science, here at the bottom, I've kind of explained what I mean by anomalies and normals. So the anomalies, you kind of think of it as a model error, your y minus y hat. It's what's observed minus the normal, and the normal being the mean over your period of interest. So I'm pulling all of my data from a data set called ERA5. It's the 5th generation of the ECMWF's reanalysis model. So it's a very, very mature, I guess you could call it a climate model that has gone through and processed so many different parameters to give us an idea of what has been in the past where we don't have observations. So it's a great, great data set. Thus far, I've been able to knock out some analyses. We'll start off with the easiest to digest are the normals for my 4 parameters. So first off, looking at, can y'all see the top of the slide here? It's blocked on mine, so I just want to make sure y'all can see up here.
Yeah, with
Yeah,
the,
yeah.
yeah.
You can see the month.
Yeah.
Okay, fantastic. So again, looking at the, starting with the normals. So these are really easy to digest. These are sea surface temperatures in Celsius around Greenland. The white areas indicate land. I only pulled Greenland's coast, so that's really my area of interest there. But kind of as expected, didn't really see a whole lot of change throughout the year in the normals. Kind of follows the expected pattern of warm waters being fed by warm water currents, and colder waters being fed by cold water currents, in the appropriate seasons. So, water's high heat capacity, especially seawater's high heat capacity, shows up here with the slow changes in the monthly sea surface temperatures. So, if anything had really spiked here, it would have been very interesting to see. Moving on to the monthly normal mean sea level pressure. These are measured in hectopascals, also known as millibars. In meteorology, we kind of use them interchangeably because 1 hectopascal is 1 millibar. So it's really a matter of preference who you're talking to. Here in the normals, you can see the semi-permanence of the Icelandic low from October to March. It's a low pressure system that helps direct some of the late season storms towards the UK and Ireland, keeps a lot of that south of Greenland. But in the spring and summer, as that dies off, you see the blue there start to build over the Greenland ice sheet. That's indicative of stronger Greenland blocking, which you would expect as the pressure there, the atmospheric pressure there increases, and again keeps warmer air to the south. So here we're looking at the normal 500 millibar geopotential heights. So this is roughly how high up in the atmosphere you are to get to measure 500 millibars of atmospheric pressure. And this particular parameter is interesting to look at from a climate change perspective because it gives an idea of how thick the atmosphere is and how strong something like the Icelandic low or Greenland blocking is or could be. So in this animation, it really shows and highlights the changes in the North Atlantic Oscillation, which is kind of an interaction between the Icelandic low and the Azores high, and how the two pressure systems kind of play off of each other to direct storm systems and ocean currents around the Atlantic basin. And it really just reinforces the findings from the mean sea level pressure. So now getting into some of the more interesting data with the air temperatures at 2 meters. This really and truly follows the expected pattern where the coldest temperatures are over the Greenland ice sheet in the winter, while the warmest temperatures are seen in the summer near the North Atlantic current. So the North Atlantic current, which you could also think of it as the tail end of the Gulf Stream as it feeds into the Canary Current, runs roughly in the southwest portion of the map. So that's where the warmest waters are, and that's kind of where your warmest air is going to be as well. So again, the normals here don't really show anything terribly surprising. So moving into the anomalies, so looking at how different the observed was from the mean. So to orient you a little bit, we're still looking at Greenland in the same area. So the coordinates and the area of the map still hasn't changed. But what I've done is I've broken it out by month. So as the animation proceeds, you're seeing each month throughout the 39 years of data and how different that month has been from the mean over the 40 years. So looking first at sea surface temperatures again, nothing really pops out except for the persistence of higher anomalies, greater positive anomalies persisting closer to the present, especially in the autumn and winter. And this is particularly alarming because that's, warm water is what's going to help move warmer air into the area. It's going to affect the melt rate or the refreeze or the new freeze of land ice in in Greenland. So it's definitely something we're looking for and trying to identify. Moving on to the main sea level pressure. So the biggest takeaways I've seen thus far, as the stronger anomalies, propagate through, it really shows stronger fluctuations and potentially significant fluctuations in some of the key pressure systems like the Icelandic low and the Greenland blocking, but more importantly, the North Atlantic Oscillation, which really governs a lot of the climate we experience in North America and in Europe. So here haven't really gotten into the details of what it means for the North Atlantic Oscillation yet, but it's really evident with the stronger anomalies getting closer to the present. And again, the 500 millibar anomalies here, largely reinforces the findings in the sea level pressure findings. So again, the stronger anomalies indicating stronger and potentially significant fluctuations in those key pressure systems. And looking at the anomalies in the air temperature, again, very similar to the sea surface temperature anomalies, seeing a lot of stronger, more persistent anomalies, especially warmer anomalies persist closer to the present in the autumn and winter. And again, that's alarming for a number of reasons, but primarily prolonging the melt season and kind of pushing back the freeze. So I have managed to get a couple point patterns done just of air temperature, and starting with wanting to look at some autocorrelation, see how it's everything's performing as expected. Well, not performing, but observed as expected. So running local Morans to just really verify that yes, indeed, warmer temperatures are near warmer temperatures. Really, it's not terribly surprising since the environment likes to like tends to be near like. One of the things I am considering though is going back through and playing with the size of the neighborhood in this particular calculation. The data is provided at a 1/4 degree resolution, so that 10-kilometer neighborhood includes a fair number of points. I'm debating whether or not it'd be worth expanding that neighborhood or not, but I know I have a number of tools to look at to see what's reasonable and what's not reasonable, and just really haven't gotten there yet. Moving on to the next one, looking at G star there, and I haven't found any extremely hot or extremely cold clusters that really persist over time near the present. But again, as I was saying with the temperature anomalies, we are seeing the hot spots clustering together and persisting in the autumn and winter. They're not extremely clustered, but they are there and they are evident in the statistics there. So again, there's a lot left on the plate to get through. To continue my spatial analysis of all the other parameters, I'll possibly look at other methods, looking at EOFs to see if there's anything unusual in the distribution, spatial distribution of the parameters. I don't believe I'll find anything there, but again, exploratory analysis. One of the, kind of jumping a little bit ahead of myself, one of the things that's fun about using R is you're constantly looking and learning how to use different packages to do what you want to do, to see if they have the functions you need. And so come across a paper describing a new statistic for spatial autocorrelation and distributions called ELSA. And it's something that I'm going to read up on and see if it's worth exploring as far as spatial entropy. So I'm also going to look into, as I said before, spatial modeling to see if there's anything interesting or significant in the coefficient surfaces, explore the relationships between the parameters, and see how they depend on space. I imagine there's going to be some spatial dependence, warmer temperatures being closer to the south and colder temperatures being closer to the north, for instance. I'm going to move into the spectral analyses and pull apart the signal and see how these parameters fluctuate over time and any particular points of interest that show up in the spatial analyses. Number of tools at my disposal for that. And then the fun bit with the spatiotemporal, putting it all together, figuring out how does it change, how does the trend in space change over time, and how does the trend in time vary in space. So my goal is to have something that I could submit and present in December at the American Geophysical Union's annual meeting. This is really right up their alley with a combination of oceanography, meteorology, climate, cryosphere, GIS. It's it's a nice little hodgepodge. It would be perfect for AGU. So challenges I'm encountering, as I said before, constantly, continuously learning new functions and packages in R. Google is my best friend. R has some significant memory limitations that I'm learning to work within and work around, but it's still proven more reliable than ArcGIS, which won't even ingest the data. But again, it's a ton of data, and running, as we go through class, you think, oh, well, something like, any given Lisa isn't terribly complex and should run in just a couple of minutes. 1 month from 1 year takes 15 minutes to process in R. So given it's almost 40 years worth of data over 12 months, it takes roughly a day to calculate one of the statistics, and that's with running parallel computing. So it's constantly a challenge to manage the hardware and software to get everything out on the back end without any sort of interruptions or crashes or freezes, etc. So big data challenges. So far, haven't seen anything terribly crazy, anything that doesn't really fit the assumed patterns and trends that I've seen in the literature. I didn't really go into depth at all on the literature. Been focusing strictly on wrangling the data and starting the analysis. I've had many discussions with one of the doctoral students. She was largely the motivation for jumping into Greenland. and its climate. But knowing kind of the rough idea of what the Arctic climate has been and what it could be in the future, and the data really hasn't jumped out and bit me just yet. So with that, I thank you for your time and your patience, and open it up to questions.
All right, Kenneth, great job. Very, very interesting topic. While we're waiting for some questions to come in, I have one for you to reflect on. This isn't a criticism, I'm just kind of throwing this out there. So the maps that you're showing for visualizations, they look like they're being projected on a cylindrical projection. Greenland, of consequence, is a landmass that's positioned in the northern latitudes. So on the cylindrical projections, you're getting the meridians being pulled apart as well as the parallels. And by virtue of that, the visualization or the visual appearance of your data is coming across differently than it would be if the spatial relationships of the graticule were preserved more. So I don't know whether you've thought about that, or because there's really two sides of this. There's the calculation of your indices, which takes place in a projected, or you could do a datum, just latitude and longitude, and then display those in a visualization on a projected coordinate system. So there's some things maybe that you could reflect on a little bit.
Sure, and yeah, in previous work that I've done in the Arctic, I have played with using different projections. And with this, kind of preliminary initial run through, I decided not to, try anything like a polar stereographic, just to just get the initial look. With running everything through R, there are some challenges with changing the projection. And the nice thing is the net CDF files come in on an unprojected surface. It's all a geographic coordinate system. It gives you all the data you need. It's not in any particular projection, so it's easily moldable and easy to project. It takes a little bit for R to catch up and do that work with so many images to process. So I'm just going to leave it alone for now.
Well, yeah, thanks for your reflection, and kudos to using R. I'm a fan.
And to Jeremy's question, did you use Arc to do the animations or another app? So I have found myself slipping deeper and deeper into the bourgeois of the tidyverse in R. As you learn more and get more involved in programming in R, Hadley Wickham's tidyverse really is almost essential to clean and efficient coding. So a lot of people have expanded upon that, and I have discovered and started learning how to use a package called ggAnimate that uses the ggplot functionality to create these animations. So it's definitely there's been a very, very steep learning curve involved in that, but it's everything you just saw was done in R. Questions are coming. So Andrew, looking at sea surface variations, sea surface temperature variations, will you be relating those to CS variations in, say, the Davis Strait or and/or East Greenland Sea? Possibly. I'll have to go back in and see if ERA5 has sea ice extent or sea ice concentration. I know NOAA does. I've played with that data a lot. There'll definitely be some issues with matching the resolution of the two data sets there, but definitely something interesting to look into. I think autocorrelation saying north of Greenland and T2 are likely to be related to pack ice in that region. Yes, absolutely 100% think so. Yeah, I haven't done much analysis up there in that particular part of the Arctic, but it definitely makes sense that the stronger autocorrelation up there is definitely related to the pack ice. Yeah. Helen, yeah, R is awesome. I started trying to learn Python and it upset me. Jeremy,
You should never start zeroing with your loops. Yeah, Python is bad, but
Python's terrible. The data frame is the greatest thing since sliced bread. And the spatial analysis power in R nowadays is fantastic, and I'm glad they finally managed to build the bridge between R and Esri, so that it's easier to port the data back and forth. I know in one of my classes there was a lot of doing the statistical analysis in R because it was just quicker writing the rasters and porting it over to ArcMap. So yes, Andrew, absolutely. Yeah, I think that's where I got my ICE data at one point. CICE index 3, if I'm not mistaken. So
I have a quick question.
Sure.
Thanks for a great presentation. And
Thank you.
how much of your how much of the autocorrelations that you're seeing in the spatial autocorrelations there, how much do you think they're a feature of the model versus how much do you think they're actually a physical thing that's actually there? Or like, for example, I know a lot of your variables are going to be autocorrelated with each other as well.
Mhm.
I'm guessing you see all of those relationships in this data.
Yes, the autocorrelation doesn't surprise me. You take a high pressure system, for instance. At the core of a high pressure system are going to be your highest pressure, and it's just going to expand out from there. So when you look at the spatial autocorrelation of a high pressure system, it's going to be highest at the center where the highest pressures are observed or modeled, and then as it goes out, it'll be less and less. So what's more interesting I've found has been the G-star statistic in identifying the hot spots and cold spots and how they change over time. Is that, to me, stands out more, showing, hey, this spot was coldest 20, 30 years ago, and then you watch over time as it becomes warmer and warmer, and it the anomalies kind of show that, and how different the observed was from the mean. But the G-star really kind of highlights that, yes, this is a statistically significant hot spot or cold spot, and this is definitely jumping out as something big that has changed over time. So yeah, G-star has kind of become my my favorite of the Lisa's.
Cool, thank you.
Mm-hmm. Catherine, adjusting the FPS, absolutely. That is something I continue to struggle with. Again, it was, I've tried slowing down the animations. I'm still trying to tweak that and make it a little easier to follow and understand. And data visualization is a constant piece of work in progress. So it's like that one road that's always under construction.
All right. If we don't have any other questions, I think this is a wrap, right? So Kenneth, want to thank you for an interesting talk, and Frank, thank you again for an interesting talk. If both of you can, again, take a look at the top of the chat window, there's the form or the link that takes you to the peer review form. If you could fill that out, that'd be great. Otherwise, I thank everyone for attending on Monday night. I know your time is precious, so the presenters did a great job, and they thank your questions and interaction. So till next time, we bid you all a fond farewell and a good night.